So welcome to the Texas Water Journal webinar. We are going to be discussing a recent paper in the Texas Water Journal that is about reservoir sediments and modeling of those sediments. And so I'm going to introduce our speaker shortly, but just wanted to first start off with a bio for our speaker, John Zhu. He is a senior data analyst at the Texas Water Development Board, and he's responsible for data processing, analysis, modeling, and assessment of surface water availability for water resource planning, development, and management in Texas. John was educated as a groundwater hydrologist at Jilin University in China and earned his doctorate in karst hydrology from the Institute of Geology, Academia Tsinghua, China. And I probably mispronounced that, John, so I apologize. Since his postdoctoral work, John has expanded his research interests into the surface water arena through research on soil water at the Institute of Geography at that same university in China and studied karst water in the Peak District of England as a research associate at the Manchester Metropolitan University. John also taught hydrology and conducted research in karst hydrology and geomorphology as a lecturer at the University of Papua New Guinea and served as the chief hydrologist at the Bureau of Water Resources at the government of Papua New Guinea. John has been leading and participating in many projects at the Water Development Board, including water availability estimating through running Texas's water availability model under various scenarios, through short-term reservoir storage forecasting by running Reservoir modeling, drought mapping, water condition reporting, lake evaporation and data monitoring, and management of the Water Development Board's reservoir database. Armed with a strong set of programming skills such as Microsoft Certified Professional, John has extensively been involved in data processing and analyzing in the surface water arena. So, John, take it away.
All right, thank you, Todd, for the introduction. I'm humbled for this honor. Let me share my slide and sharing. Okay, and done is a slide show. So you see my slide?
Yes, I can see your slide.
Okay, thank you very much. Yeah, very pleased to have this opportunity to present our work at the Texas Water Development Board. Actually, it is on a teamwork. It involves my colleagues, Fernando, Holmquist, Nathan Leib, and also Carla Lucille. And most of them are on vacation or have some other thing to do. But today, Holmquist is here, and she is our hydrologist, GIS specialist, has been working for lake survey for more than 20 years. So anything related to lake survey and sediment, Holly may help me to answer any question. Holly, yeah, great, turn on your camera. Okay, and others are on vacation anyway. I have to read a statement here. The statement contained in this presentation are my current view and opinion, and are not intended to reflect the position or information from the Texas Water Development Board. No, it can remove. Nor is it the indication of any official policy position of the board. Yeah, and my presentation topic is projected reservoir reaching curve and their utility for the water planning for Texas. Yeah, so the overview to my presentation here is first we will have an introduction including the statutory requirement and then the current situation for using this reservoir reading curve. And then we will start from the sediment distribution in the reservoir to as a foundation for our new method. Then we will discuss this new method for estimating the future reservoir reaching curve. And then we will briefly discuss how the application of this projected reaching curve. Finally, we have a comparison with the popular traditional or empirical method. And then we will finally conclude this presentation. So first about the statutory requirement, the rule of water planning in Texas. Texas Water Administrative Code on a chapter 357.10 require the regional water planning group in Texas to use firm yield under repeated drought of record using anticipated sedimentation rate for estimating the reservoir water availability. And so by this rule, the reservoir reaching curve must be used in the simulation for firm yield by in Texas, it's a common model called water availability model. So that is the law. The law says using sedimentation rate, then Texas Water Development Board, TWDB, have a guideline for planning, and that is in the Exhibit C. And this is stated clear. The state that regional water planning group shall modify TCEQ water availability model using the latest hydrographic survey and projected future capacity and reaching curve in order to more accurately reflect the firm yield for the planning period. So here is the requirement. They will have to using this by this guideline. And what is the firm yield? The firm yield is the maximum annual diversion from a reservoir or reservoir system. That's the 100% reliability during the entire period of the simulation. The firm yield will guarantee the water has never shortage during whole period. That is the legal requirement for. And so how in the past or near recent term, how the people using this the method to estimate the future reservoir reaching curve. So most of the regional water planning group are using general overall sedimentation rate, because each reservoir have a sedimentation rate overall, say each year 200 acre feet or something like that, right? And then using the empirical method to estimate the future reservoir elevation area capacity reaching curve. We often say EAC reaching curve for estimating firm yield through dam simulation. And the most common method currently used, almost all the groups are using called area incremental method. This method, assuming the sediment taking the equal area along the entire vertical elevation of a reservoir profile to achieve the overall sedimentation rate by adjusting the area, but this area is the same for all the elevation. Then finally, we compute the reservoir volume by trapezoidal or conical formulation to achieve the sediment goal, for example, 200 acre feet, finally, or something. And this is a very traditional, a long time ago, developed in 1953. And there are, after that, there are some other similar methods, but all the empirical methods. And so the first method I just mentioned is equal area along all the reservoir elevation. But some people say no, because some reservoir in the mountainous area, they have a higher sedimentation at a higher elevation. And some other area in the flat plain, and they have higher sedimentation at the bottom portion of the reservoir. So they developed 4 types of curve. But it is still anyway a theoretical thing. And so the formulation is look like this, and they have all have their constant. And others are similar, like later on in 2009, someone changed the relationship to be a logarithm area depth relationship. So until now, all this empirical method, assuming the sediment with a particular formula or equal sediment area reduction. So let us check the Texas reservoir, how the sediment distribution. And then luckily, TWDB have a lot of lake survey data. So in Texas, the first sediment record is 1889, and that is on in the real ground catchment. Then the first reservoir sediment study in Texas is 1893 to 19,000 and 1900. That is by University of Texas, a certain author called Taylor. They studied Lake Austin and found that 48% of capacity loss in 7 years. So original Lake Austin without any other dam, it's very higher sedimentation rate. But later on, many other lakes were built upstream. So Lake Austin may not have this type of sedimentation rate. And later on, in 1991, Texas 72 Texas state legislature authorized the TWDB to form a hydrographic survey program. And I think after that, Holly was hired. And so since then, Holly had been working. So since then, hydrographic survey program has done around 200 survey for about 120 reservoirs. And in this 120 reservoirs, there are 60 survey, not only bathymetric, also include the sedimentation survey. So-called sedimentation survey is they will pick up the sediment sample and to measure the sediment depth directly. So that is the situation. So let us see how the sediment distributed in the reservoir in Texas. I just pick up several common examples. First is the Lake Buchan in the up or middle Colorado River basins. You can see a lot of sediments in the upstream, but not all upstream. Somewhere, anyway, in the up section, there are more sediment. And then another reservoir, Eagle Mountain Lake in North Texas. You can see a lot of sediment basically is concentrated near the dam in lower portion. But I'm not meaning it is a smooth curve up and down. And then I give you another example. We pick up another example, then like Lake Fork Reservoir, also in North Texas. And there are two arms of the reservoir. And on the western arm, you can see more sedimentation in the middle portion, probably caused by the tributary running in. And another one is Lake Wickle in central Texas. Also two main arm of a reservoir, and in the southern arm, it's a lot of sediment. And also you can see at the lowest portion, there's some sediment, but also in the middle, there are more sediment. So checking into the detail, we can compute the sediment volume at each elevation interval. So here is the plot for other reservoirs I pick up here. One is Lake Camp. And you can see for each elevation, the blue bar is the sediment accumulation volume. And then the red line is the area reduction. So higher sedimentation and higher area reduction. So anyway, and another one, Lake Grip 1, is in the bottom section, a lot of sediment. And then in the middle, upper middle, less, and then suddenly get more sediment. And then is regular salt. So the area reduction is up and then down and then up suddenly. So that's the situation. Proctor in the central Texas in the west portion. So there are several peaks of sediment here, and then at the top section, there are more sedimentation. The last one is Lake Worth in DFW area. And you can see that is in the bottom, there's some sediment and then absent sediment, and then basically it's a two peak. So what we can see by all these examples is sedimentation in a reservoir, it can accumulate at any elevation, and it is varied. It depends on each reservoir's situation. Yeah. So by this finding, the sediment distribution reservoir is highly variable in the space, especially along the vertical elevation. So by this finding, we propose a new method. We call this method is elevational volumetric sedimentation rate method to estimate the future reservoir capacity and elevation area capacity reaching curve. So the details about the method is that we must have two surveys for one reservoir. One is the older survey, one is the newer survey. And the two surveys, because in older time, the reservoir is relatively larger, and then with the sediment filling, it becomes smaller. So we take an example by Lake Gringer, we call it Gringer Lake. And the sediment is in the middle and lower portion. But it can be anyway. So what we do is for each elevation interval, and I make it here very large, but actually it's very small, just about 1 inch, or say 0.1 feet interval. So for each interval, we compute the sediment volume first. So it's all the survey volume in this interval minus the volume of the new survey of this elevation interval. So we know how much sediment was filled in this elevation interval, and then divided by the survey interval. For example, this one, the first survey is 1995, and then in 2013, there another survey, the red line. So this is the two survey, and that is two existing reaching curve. So we compute the sediment volume for each elevation interval. So we got what I call sedimentation rate curve, but it is volumetric reaching curve. You can see that for each 0.1 feet elevation, the sediment volume is look like this. Over here is the highest is 1.8 acre feet. Then it is coming down and starts from here, finally go up around 1.2 acre feet and going down and going up. And finally, near the top of conservation pool, there is no sedimentation. So that is our methodology. We using the actual sedimentation volume at each elevation interval, and then we using this rate to compute the future reaching curve. So here is the same reservoir, and the solid line are survey. So we take the survey 1995 and 2013 survey to making projection for the future, the broken line over here for future planning period. Planning period is 2020, but that was last planning cycle. For current planning cycle is 2030, 2040, 50, 60, 70, and 80. So the reservoir becomes smaller, but this is the reaching curve we did by this method. We call it projected elevational volume reaching curve. Then for area, it follows the volume because the area will equal to the last area minus the sedimentation taken area. And then this area, how can we do is that the sediment volume divided by the elevation interval. So we got area reduction for the future reaching curve. So we got all the future reaching curve. And this is using for VM. We have to extract because VM is a program and only taking 12 elements for the future reaching curve. So over here, the first 4 line is for 2030. We have elevation and we have volume going on, and then area, corresponding area. The VM actually using the volume and the area only. They don't care about elevation, so that didn't come on out. But in order for reader to read our reaching curve, we keep all the data. We also give clear what capacity it is and how the data pool is. So for each decade, we have all this data. And you can see at the top of reservoir in 2030, that is 48,000 acre feet. And that's 46, 44, 42, 40, and then 39. So down to 2080, this reservoir will be much smaller. And the bottom elevation is going up. And you see elevation 478.6 in 2030. But when you go up to 2080, that will be up a lot, 487. So almost 10 feet has been filled at the bottom of this reservoir. And so that is the reaching curve. And then we can using this reaching curve to compute the firm yield, simulate the firm yield by the TCEQ water availability model running 3. And then we got all the capacity and firm yield relationship. And above here, that is actual capacity. And for over this area, this our projected reaching curve. So the capacity going down and the firm yield also going down. Yeah. And then we can also compare with the time. The timing is from 2030 planning to 2080. The firm yield is going down like this, and that is computed by actual capacity. So that is the method and how we use it. So it is, I think, highly curious for how it compare our method with the popular empirical method. So we using one of the methods, the area incremental method for trapezoidal shape. So the red line is the projected reaching curve for Lake Granger for 2050. Then, we have 2050 reaching curve too. So that blue is our reaching curve. And at the top of conservation pool, the total sediment is equal. So the capacity for both methods are the same. However, if you go down to the reservoir, the reservoir volume is higher than ours. So this is the projected reaching curve difference. And then how about the firm yield? We compute by these two different reaching curves. The empirical trapezoidal method is the right point for the firm yield from 2020 to 2050. The last graph I show you is over here, 2050. Others, I don't need to show it for clear presentation. And by our method, we compute firm yield is significantly smaller than that. So that is the difference. So what we can conclude over here is our method, the East Reservoir specific sedimentation rate method based on two hydrographic survey, one old survey, one new survey. Or if the reservoir is sediment survey, one is good enough because to take out the sediment, Holly can get the original reservoir capacity reaching curve. So we can compare that reaching curve, that capacity with the latest survey capacity. We feel this, what that is, I should say, I feel this, the method is a higher accuracy over other empirical method for projecting reservoir future reaching curve. And also for the convenience of water planning, we did for altogether for 80 reservoirs based on the availability of the reaching curve. And this is posted in the TWDB website. So anyone, for your convenience, you can just go down to the website, selected reservoir and copy paste all the evaporating curve into the model. Then you can get the firm yield easily. So that is my recommendation. And the reservoir owner and regional water planning group to consider using this projected region curve for computing future firm yield in water planning processes, unless a better alternative method is found. And then the traditional method, empirical method, other method, maybe still other published method, maybe still can be used if we don't have the region curve. And because this method is based on the survey, so we recommend the reservoir owner to conduct a lake survey at least once every 10 years for better estimate reservoir sedimentation rate and therefore the firm yield. So that is basically what we're doing. And so what my suggestion is like this old proverb that the proof of pudding is in the eating. So I suggest you try these processes and to use it, and then you understand how the sedimentation and how the raising curve can be done. Thank you. Any question?
So if you have questions, you can enter them into the Q&A, which is down at the bottom of your screen. You should be able to click on that and uh, enter your questions there. I've got a couple of questions, John, and maybe Holly. This is a opportunity to bring Holly in to help with some of these questions. The first one that I have is, looking at many of the charts that you had for the reservoirs, you see the peaks of sediment, inflow, and I'm guessing, are those, you know, related to high flow events? I mean, do you try to match any of those peaks up with changes in inflow?
I think you're right, Todd. I think the flow is one of the main factors. And also, I think in the area of physical geography, for example, one of a tributary, they are running in the loose soil and easily causing erosion. So when any storm water, a larger rainfall, they can bring in a lot of sediment. And this sediment really depend on where it's coming in. If it's in the top of reservoir mouth, river mouth, and then it will deposit at a higher elevation. However, if it's coming in the middle from tributary, it may be deposit at the middle area. So it is highly variable. And that's why we made the project reaching curve by considering actual sedimentation spatial distribution.
Well, to me, it seems like just having observed a lot of floods, and of course the recent flood, you can see where uh, all there's just a massive amount of sediment being moved downstream, and it seems like it's probably a fairly good match with those peaks. The other thing I wanted to ask you is, comparing your methodology to the one that you compare to here in the presentation. Seems to me that it indicates that the firm yield may not be what we thought it was. It may be less, and that is probably something that the regional water planning groups will need to take into account. I may be misinterpreting that, but I'm curious about your thoughts on that.
Okay. I think my thought is just one comparison, and fortunately or unfortunately, is that method give a higher from yield, and our method is smaller from yield. But maybe opposite, we do not know. And I think because the projected reaching curve is a difference, so it must be causing the firm yield difference. As which value is larger, which one smaller, so sorry, until now, I don't have more evidence. Uh, so that's why we are trying to do something in the future to compute all the firm yield, and then we will know which one is higher, which one is smaller. And on your thing, I think about the flood, the peak, I think Holly know more about it. I think after major flood, it will accumulate a lot of sedimentation. And I think so that's why sedimentation rate is a general, sometimes that may be higher rate, sometimes maybe lower rate. What we are talking about is a general sedimentation rate for past certain time or period. And we deem that as a concern for the future. Holly, that's right?
Yes, John, it's our sediment rates are an average over time. As you were talking about the high inflows that we've experienced recently, and you can see how much sediment is in those rivers just by the color of the water. One of the challenges with that is if the reservoir water levels are significantly low, that sediment's going to deposit at a different elevation than if that reservoir were high. And we tend to see that the water follows the historical river channel and flows through the entire reservoir. So, different sediment is going to drop out at different times based on the weight of that sediment. And sediment can be redistributed. So it's not just a matter of accumulation when there's a high flow. So it's very challenging. And the average over time, there may be one or none or multiple high flow events during that time span. So
Thank you. Thank you.
So I have one more question, and I haven't seen any questions in the chat yet, but 100 years ago when I was an undergraduate, I was reading uh, something in college, and it was discussing construction of reservoirs in other parts of the world and sedimentation rates, and it often said something like, okay, this reservoir is built, and then up in the watershed above it, all of a sudden there's a lot of agriculture that all gets started all of a sudden, and a lot of that big change in land use practices results in a lot of sediment going down in the reservoir below it, and it reduces the useful life. And so I was just thinking a little bit about what could be done if you're, for example, the Corps of Engineers or you're a river authority and you're worried about sedimentation rates and you want to slow them down, or maybe even the Water Development Board, if there's a possibility that you could, try to pay farmers upstream, maybe to have barriers along, between their fields and the streams, or maybe not to use certain methods for plowing, like to go to zero, till or I mean, it seems like that there could be, some uh, systematic way to reduce sedimentation if we're, keenly concerned about this reducing yielding these reservoirs over time, seeing how, their yield is, uh, you know, pretty important to maintain into the future. And so I'm just curious if y'all thought about that.
Yes, that is a great question, Todd. I think first thing first, we fully agree that the environment somewhere may be changing. So somewhere maybe has more farm agricultural land. So they cause higher and higher and higher sedimentation. But some other area maybe have a higher reclamation, and so the sedimentation become lower, or when the inflow become lower and lower. So I think Holly had an example, but later on I will give her time. So that is one thing. The second thing is that the human, in order to solve this sedimentation problem, there are some owner already using the method called dredging. They take off the sediment regularly. I know one of the lake is called Lake Leber. The sedimentation is taking some of the volume down. So the owner hire the dredging company and to dredge it. So I think this is also our future thinking. How can we solve this dynamic environment, dynamic problem? Yeah. So Holly, maybe you can talk about the Possum Kingdom have that problem, right?
Yeah, so our example in Possum Kingdom, we noticed that the sediment rates were much higher when it was first built, and it sort of slowed down over time. So it seems that when reservoirs are first built and the dynamics of the river channel changes, that it creates a higher sediment rate into the reservoir during its first, first whatever years, can't really say. No, I agree that, some sort of watershed mechanics to reduce sediment would be great, but that's not really our scope. Yeah, like John was saying, there are reservoir owners now resorting to dredging, but you have to consider those sediments may or may not be viable for other uses. So it's definitely a challenge. And we do have, I know in our group, we have recently contracted to have sediment studies conducted just to find out what has been done in the past, so we can kind of plan for the future on what we might want to do. So currently we don't have massive amounts of funding for that type of thing, but it's a study we are conducting. So
Thank you.
Well, we don't have any other questions, so I think that's it. Unless I see one pop up in the Q&A real quickly here. But John, I want to thank you for a great presentation today, and a nice bonus to have you, Holly, to be able to join us as well. The goal will
Thank
be,
you, Holly.
yeah, thank you. The goal will be to have this webinar posted on the Texas Water Journal website in a week, maybe less. And then anybody can go ahead and watch it again along with our other webinars. This is our 9th webinar so far, and we are trying to put together webinars for our authors as our articles come out, for those authors who are interested in doing a webinar. So
thank you very much. Thank you everybody for attending my presentation. And if anyone have future questions, you can send me email. So we keep contact, keep discussing, keep improving our method. Thank you.
well, thank you. And I guess that's a wrap. So look, in the next couple of weeks for notice about another webinar that we'll be doing, probably in September. But until then, thanks everyone. And thank you, John and Holly.